Hi everybody, I'm Aviv Zohar. I'm a professor of computer science here. I actually attended the summer school as a student a few times. I did my PhD here. And it's responsible for some of the credit points for my PhD, so even that. I'm going to talk to you about the economics of cryptocurrency mining. Unlike maybe some of the previous talks that opted for depth, I'm going to try to be wide. And so a lot of the stuff I'm going to say, I'm going to err on the side of being too simplistic. And my goal, if I succeed, is to show you there are a lot of interesting economic questions hiding inside this protocol. Today we're going to spend some time on the aspect of cryptocurrency mining. And tomorrow, in the second lecture, I'm going to talk about things that happen within blockchains, mostly within Ethereum, in smart contracts, and what that ecosystem looks like, and what are some of the interesting things that have come about in that area. So before I get started, I want to know kind of what you guys know. Who understands how the Bitcoin protocol works? Raise your hand if you know the protocol and understand it.
Define
understand means you know what proof of work means, you know what the longest chain rule means in any way. So maybe like a third, a half. Okay, so I'm gonna, I have to do this, I have to give an introduction to the protocol, unfortunately. This usually takes me 2 hours. I'm gonna try and rush through it. Because even after 2 hours, people who hear the protocol don't necessarily digest the consequences and meanings of everything. So I'm going to try to do a quick version of this so I can get to the economic aspects later. And hopefully everything I say will be trivial. So feel free to jump in with a question or an opinion or clarification if you need it. Right, so I'm going to try to go for the explanation of the protocol. Then I'm going to talk about mining equilibrium. I'm mostly going to devote time today to this classical old style proof of work cryptocurrency stuff. And then I'm going to show you many ways in which the protocol is not in equilibrium, which is kind of disturbing in the deepest sense because nobody should be following it. And then if we have time, and I'm not sure we're going to have time, I'm going to talk about mining and risk. And again, it's all about cryptocurrency mining. So let's jump right into it. So the way I like to explain money to computer scientists is from the computer science perspective. And there's actually an economics paper with this title, Money is Memory. So if we think about money technology, it's very old. This is an old shekel coin. It's, I think it was made of silver. It's a rare metal. So this technology of money is ancient. And there's something very nice about money is that this token, in some sense, represents memory. The person that holds it, somehow, we think of society owing him something in some sense, right? If the red agent gives a service or a good to the blue agent, he pays him with the token. The token itself doesn't do anything, except in some sense we remember that this guy, we owe him, somebody in the future will give him a good and he'll pass on the token. So we can say, the people who are holding tokens in some way have given to others goods and services, and they're due sometimes in the future to receive something in return. So that's an interesting way of looking at money, right? But it's a form of memory, and the nicest properties of these things are that when you give it, then it's a rare metal, right? So you can't produce as many of these as you want, and once I give it, I don't have it, and he does. And it stays around, it doesn't get destroyed. That's a good property of money. So that brings us automatically to today, right? We have digital means of moving money around, but information doesn't behave like matter in the sense that when I send it, I can keep copies of information. So you can't transmit data and expect that to behave like money. So the model for electronic cash actually introduces a third party which records in its memory, right? Again, money is memory, records in its memory how much money each participant in the system has, right? So I draw a bank here, but really it's a computer somewhere in some basement, or a lot of computers maybe, and they have records of accounts, And now when we want to transfer money, what we do when we transfer money on our phones or whatever, we send a message, a digital message, to the bank requesting to change the balances of these accounts. And that's a transfer of money. It's no longer this physical thing. And the wondrous properties of this were that it was very hard to disrupt. Like if somebody wanted to stop me from transacting, they had to physically be there. They wanted to know that I paid somebody, they had to physically be there and see it. So it had kind of this built-in privacy. Nobody would take fees from this transaction. Whereas here we have a point of intervention where we can stop the transaction. We know that it occurred. We can follow all the transactions. Our money is not really controlled by us, right? The bank, what happens if the bank just erased my balance? That would be catastrophic for me without my permission, or would freeze my funds, or would refuse to let me move money and so on. So now this is where governments started regulating banks to make sure that they don't do any funny stuff. Of course, there's a lot of different kinds of regulation, that they don't loan too much of their money and so on. But even at the very basic level, that they just manage funds as we ask them to. And this is where I think Bitcoin comes in. It looks at this third party and it says, this is a strong kind of bottleneck or maybe intervention in my freedom, and I want to take this machine and I want to make it weaker, right? So what does it mean to make it weaker? I'm going to introduce competition here. There are going to be a lot of computers here. Together as a system, they will emulate the behavior of the bank. I will send them digital messages requesting to move money from place to place, and they will comply. But the system doesn't depend on a single computer here. If one of them misbehaves, takes my money away, refuses my transactions, whatever, the others are still going to help me and comply. And this network of computers is going to be spread around the world in many different jurisdictions. So if somebody comes with a court order and tries to confiscate my money, they won't be able to do that. Okay, so in order to emulate the bank, these machines actually replicate the information of what's in all the accounts. So this is not a cheaper alternative. It's more expensive because it copies all the data and repeats all the work, and everybody checks each other's work. It's much more complicated, and it's going to be slower and worse in many, many different aspects. As a computer system, this is it looks like a bad idea, but from the economic perspective or distribution of power, these are all going to be weaker players. Okay, so are we okay up until now? All right. So now we come up to the problem of creating this system instead of this one. And that problem is that we need to agree about the balances. Otherwise, the system doesn't work really well. And one of the bigger issues here is that when we're dealing with money. So if you manage to confuse the system, to make it misbehave, you can potentially make a lot of money. You can make yourself rich, right? In some sense, we can't trust any one of these to become the bank because they'll just increase their own balance and they become rich, but because they're maintaining in their memory how much money everyone has. So we have to do something more sophisticated. And one of the most interesting attacks somebody could have on the system is what happens, right? We have to answer this question of what happens when someone that has money, right, like the blue agent here that has 2 coins, and sends them all to someone, right? Let's say he pays to the red agent, he sends this message to the system, to some of the computers, and he sends a different conflicting message where he sends all his money to someone else. Is he going to get away with, the red guy thinking that he got money, at least for some of the time, and the green guy thinking that he got money at the same time? Okay? If we manage to send this to one machine and this to another, and even for a brief instant, one of them thinks that they got paid, what's going to happen? You're going to walk into their store, they think they got paid, they're going to give you, a laptop, and you're going to walk out, and then maybe later they figure out they don't have money. Okay, so this problem is called double spending. If you can use the money twice, it's not good as, it doesn't have the properties of money that we'd expect. The problem here, again, is made worse by the fact that this we're trying to have this as an open system. The system is open on purpose, so we don't have a single entity that decides who gets to participate in this network. We want everybody who wants to join to be, we want them all to be able to join. So some of these machines are actually working with this guy who's trying to confuse the system. They're working against us in the sense that they will send messages that are off protocol. They'll try to confuse us. They'll try to misbehave. Do whatever we can to get this red guy maybe to think that he got paid and the green guy to think that he got paid at the same time. Okay, so that's the problem. And from the computer science perspective, this is called the consensus problem in a permissionless system, in an open system. And this is actually something that was thought to be an impossible thing to solve. And there's a paper by Rafael Paz proving that it's impossible to solve until you introduce something that was, of course, outside of the model for the paper, which allows you kind of to circumvent this impossibility. Consensus protocols in themselves are very interesting and non-trivial. I think the permissionless part is what made them hard, because in regular consensus protocols, you use kind of a majority vote of the participants in the system to decide, whether this transaction happened or this one. But here, because the system is open, we don't know how many participants there are. The attacker could be overrepresented, so we don't have a notion of majority. It doesn't exist there. Okay, so now I'm going to get to what cryptocurrency mining really is. And there is a misconception in the media, right? If you go out to the public and you ask, why is Bitcoin worth anything? They tell you, Bitcoin is worth a lot because there's some computer that works really hard at mining it and creating it. And it's total misconception, because I could also argue, I've just dug a really deep hole in the central lawn of the university and worked really hard at it, so it must be very valuable. Somebody will buy it for a lot of money because I worked hard. Obviously, that's an economic fallacy. So I have to explain to you, why do we need a machine that works really hard, and how does it help the cryptocurrency, right? So that actually comes in to help us solve this problem, right? This is the big problem that was thought to be unsolvable. Okay, any questions thus far? Yeah.
Can you expand a bit on why consensus is unsolvable? What do you mean?
Why is it unsolvable in this scenario?
Yes.
So the problem is that anything, the impossibility is a little hard to show offhand, but every time you try to do something, you find out that it can actually be used against you as well, right? Like, let's say this message was sent out to this node, right? So you say, okay, this blue guy has money, I should change the balance, right? But then you say, wait a minute, maybe another message was sent to somebody else, he changed the balance in a different way, I have to talk to him, right? So let's say now we talk to each other and we see two different messages. So we say, okay, which one should we accept? Maybe we should accept the one that was sent first, I don't know. So now, I don't know which one was sent first. Whatever is written on the message, whatever timestamp is there is meaningless, because I could write anything. The attacker could change timestamps. This guy could actually be working with the other guy. He could have changed the message, right? So we start to get to the point where we say, okay, maybe we should cancel both transactions if we see two of them. That's also a bad idea, because if I wait, what does it mean to cancel a transaction? I'm probably going to say, if up until a certain point in time, no conflicting message showed up, I should accept it. Otherwise, I should, a conflicting message shows up, I will reject. But then an attacker will wait up until the deadline. Just before the deadline, he'll send a message. Some of the computers will think that the deadline has passed. Some will think it has not. Because messages don't arrive at all of these machines at the same time. They arrive at different times, so they start the clock at different times. So this problem turns out to be really hard. There's, I think, a Turing Prize for solving it in the restricted setting where you know who the players are, right? And formulating the problem, of course, and so on. It's non-trivial, even when we know who the participants are. And maybe I'll give you like a flavor of how it works in a restricted setting. Usually you wait for like a super majority, like if you get 2/3 of the votes saying something, you can trust that it's okay. Why? Because maybe this is going to be immune up to 1/3 of the participants being evil. because 1/3 of participants can vote, can tell you I'm voting this way to one machine. They can tell you to another machine I'm voting this way, but they'll never get a supermajority of over 2/3 without there being enough honest guys in there. So this is a little hand wavy, right? But this is really an interesting problem. So I want to show you the solution. The solution, of course, includes our buzzword there, right? The blockchain. And the blockchain is just basically, before it's a solution, it's just a data structure. Okay, it's just a way of serializing the actions in the system. So what's a blockchain? A block is basically a collection of transactions, of requests to transfer money that we included in the system. And we chain these blocks by including a cryptographic hash in each block of the predecessor. So the way to think about this, if you're not a computer scientist, this identifies the previous block. You can think of it as a pointer in some sense, right? So I draw arrows going back in time. This block follows this one. It includes the cryptographic hash of the previous one. It's a very short string of bits, just proving to us that this was created after this. Okay, and I won't get into more than that. And if you think about what the blockchain is, it's basically the sequence of all events that happened in the system since its beginning, since its inception. Right? So what's that good for? If we start at the beginning and we follow the blockchain, we read all of the transfers in order, they're all sequenced. We can follow the money as it passes through accounts. And so if all of the computers in this Bitcoin network agree about what the blocks are, then they agree about the state of all transactions, and they agree about the state of all accounts that basically is implied from that. So this is a log of events. And if you drop offline, you come back online, somebody will give you the missing blocks. You just change the balances, and you've caught up to the rest of the network. Okay, is that clear? So now, the problem that we have is that we want this data structure to grow as time progresses. We want to add new blocks that will add new transactions. And remember, we have now a network of computers that are in charge of the protocol. So we need somebody to create the block. And we can't have it be decided from above. We have to have some process that decides who gets to build the next block. And if we're not careful, the thing that might happen is that we might get two blocks created at the same time by different participants in the system. One of them might include this transaction giving red's money to blue, and the other one maybe received the conflicting transaction giving red's money to green. So now, if we think of these as histories of events, we have to choose which one we're adopting, and we can't have both of them because we can't have the blue guy thinking he got all of red's money and the green guy thinking he got all of red's money. Right, we have to choose one. So this is the double spend problem. Again, it manifests in the blockchain as a fork in the chain, representing two alternative histories. But if we pick one of them, it is going to be internally consistent because this block is legal only if red has money to give to blue, and otherwise we couldn't have included this transaction inside. Okay. So now. Basically, Satoshi Nakamoto, this mysterious creator of Bitcoin, had an interesting solution that added an interesting primitive to this problem. And his solution, I can summarize it, maybe basically by these three rules. The first rule is to make block creation really, really hard. This is we find an arbitrary, almost meaningless computational task that you have to complete, and then your block is legal. Okay, only if you've successfully solved it. So this is artificially inserted there, but on purpose. And the second thing that you want to do is once you create the block, you send it to all other nodes in the system. This is obvious, so they see the history. And now, if there is a situation where you have two conflicting blocks, a fork in the blockchain, you're supposed to adopt the longer chain of the two. Okay, the one that's longest. And the intuition behind that third rule is that in some sense that represents the majority's decision. Every block was really hard to create, so if it's longer, that means more computational power was invested in creating it. And these three rules together are the thing that's going to give us the security of the protocol.
Question about this?
Yeah.
Why does anyone have the incentive to create a block?
We'll talk about that in a second. That's going to be really important.
And
That's where economics considerations are really going to go in.
And the second question is, what if there are two chains of equal length?
Then you just keep the one that you saw first. That's a tie-breaking in a sense. And an important one.
That who saw first?
Every computer received one of the two before the other, right? And they keep and so there's an alternative, and they maintain that the current state of accounts is whatever they saw.
But different computers saw different ones.
Yes. So they will disagree
block
at least
chains.
momentarily. Yes, that's going to come.
Okay.
So you're jumping ahead a little bit.
Okay.
Let me
All right.
first finish this. Yeah.
What is the motivation of the nodes?
So maybe I'll give you like the quick headline. We're going to pay them a ton of money whenever they get to build a block.
No, they are not miners. If they're not miners, what are they doing there?
If they're not miners, they might be, interested in just looking at whether a payment is getting in. For example, an exchange that trades bitcoins for other things could be a node that is not a miner. They're looking at transactions because they're interested in whatever goes on and whether they receive money or send money successfully. I actually have a Bitcoin node running on a computer at the university. It's not an expensive thing to run. It runs you can run it on a regular laptop. It's not pricey. The problem is creating blocks. If you're a miner, that's the hard work. Then you need like data centers full of computers to actually turn a profit. But to be a node is very cheap. You can actually have a Bitcoin light node that doesn't follow this entire blockchain, but just selected parts of it on your phone. Right? It's also possible. So if you want to send a payment, you don't really need a very strong computer. Yeah.
Sorry, the new block is always longer than the previous block.
So the new block, the blocks are of limited size. They have a fixed size. It'll point to the previous block. It's always built on top, right, of a longer blockchain.
And it includes all the information about all previous transactions.
Right. So this hash, in some sense, encodes a commitment to the previous transaction. It's not exactly all the information. This is just going to be 256 bits, but it depends on all the previous transactions. So that if somebody changes one of the transactions here, this would no longer match, right? So in some sense, this is a data authentication scheme of sort. Yeah.
And the chain does not have a maximum length, right?
No, it actually grows forever. It will keep growing. Okay. Excellent. So what's the problem, the computational problem that we're supposed to solve? Here's the problem. You're supposed to compute the cryptographic hash of the block, the very same one that you include here, but and then you look at it. This basically outputs a sequence of bits that looks random. This is a deterministic function, but it's designed to output bits that look random and that we could not guess without actually executing the function. And this, we think of it as a number in base 2. Okay, so this is some number. And we want it to be below a certain threshold. What do I mean below a certain threshold? I want, right, this number is really small if there are 20 zeros here or 70 zeros actually, if we think about actual difficulty of the Bitcoin blockchain, like 70, 75, something like that, zeros, out of 256 bits, right? So that's, if we think of these as distributed randomly, right, they're not, they're deterministic, but they behave as if they were random, then we'd have to make a lot of attempts to create blocks and then compute the hash to get a really low number, right? So usually we would fail. So what is also built into a block, there's a field called the nonce right here, that if the hash doesn't match a low number, you change the nonce randomly. You're basically guessing. And then you recompute the hash. And if you're lucky, you had a lot of zeros here. It's a small number, and this is a legal block. So if you think about what is the action Bitcoin miners are always doing, they're changing this field, computing a cryptographic hash, checking if it's a small number, repeating, right, 2 to the 70 times or something like that, maybe a bit more. And if they're successful, they have a block, and it's actually very easy to verify that it's a legal block because you can repeat this computation, you just see a lot of zeros and you're fine. Yeah. So like a mining machine would be on the terahashes per second. The entire Bitcoin network much more. Has millions of machines mining at terahashes per second.
So how long does it take to find, like, for the whole network to find, like,
Okay, so that's a good question. That's my next thing I want to say. The difficulty of this, we can basically fine-tune it by choosing the threshold, right? So the difficulty is set so that we have a block per 10 minutes in the entire network, and we adjust it every 2016 blocks to try and match that. Okay? So now, I want to skip a little bit ahead because I'm running out of time. I'm going to skip this slide, which gives us intuition. So here's our problem. We're back to the double spend attack. Let's give the intuition on why it's actually solved it. So the problem is that the payment can be reversed, right? If I tell you, when you see a conflicting chain, you should accept the longer chain, right? Our problem is that if we see a transaction, and we don't think of transactions as accepted if they're at the tip of the blockchain, because it's very easy that to create an alternative block here by a miner, by a rogue miner, which will maybe overtake us, and we'd have to choose the alternative chain. So we only think of money as accepted if it's somewhat deeper in the chain, in the sense that the blockchain has grown. So maybe we had a payment, it got in, then 10 minutes passed, another 10 minutes, another 10 minutes, and so on. And now we think of it as slightly more secure. It gets more and more secure as the deeper it is. The thing we are afraid of is that an attacker would show up and take our money away. If I'm the blue guy, I thought I had money. Then somebody said, wait, I have a longer blockchain that I now show you. It has a conflicting transaction that sends the money that you thought you had to another account. Okay? And everybody in the network now adopts this. Okay? So that's the worst thing that can happen to us. And now we have to say, why doesn't it happen? And the reason is this, maybe just intuitively, right? This was unknown to us before. Unknown to us and also unknown to the rest of the honest participants in the network. If they knew about it, they'd have told us earlier, right? We'd have known. But now, what does that mean? That every time an honest participant was working on a block, he was extending this chain. And so they were solving this cryptographic puzzle at a certain rate. All of the computers in the Bitcoin network, a lot of them, are extending this at a certain pace. And the attacker alone is working in secret on his chain, trying to get it longer. But solving each block is really, really hard. So he could get lucky and guess, for a block or two, maybe find them faster than expected time. But if we've waited enough and we're deep in the chain, this grows pretty much according to the expected rate when all of the computers in the network are trying to extend it. And this, if the attacker is weaker than all of the Bitcoin network combined, will grow at a slower pace. And we can give a probabilistic argument, basically saying that the chance of block replacement, even with an attacker, as long as the attacker has less than half of the computational power, this is going to be decreasing exponentially as this chain grows. Okay, that's because of the proof of work. So this is why it's there. The hard work is to prevent attackers from voting in the protocol many times. Okay? And disrupting it. This gave us security from double spend. Okay, so Satoshi had a theorem in his paper. As long as the attacker controls less than half of the compute power, probability of block replacement decreases exponentially fast. It wasn't exactly proven correctly, but it was fixed later in many, many versions. And people are still analyzing the security of the Bitcoin protocol. We just had a paper, accepted this last month on a slightly more nuanced analysis. Okay, so this is an interesting, non-trivial result. So now we get back to incentives. Why would someone do such a hard computation just to create a block? This is what a miner is called. Yeah.
Well, what's to stop the attacker from spreading the false block and tricking other nodes, honest nodes on the network to do the computation for it?
Okay, so think about this scenario. Let's say before these blocks are created, a false block appears. And maybe it's extended by others. But now I'm the blue guy, and I don't consider money as having been accepted if it's not deep in the chain. So I see this, it's depth 1, and there's an alternative payment, which is even maybe on a longer chain. So, I didn't get money.
So you're not going to spend money.
So I'm not going to give you the laptop. You walk into my store, you paid me. I'm saying, okay, the transaction appears as pending because it showed up in the blockchain, it's not deep enough.
Okay.
Once it is deep enough, and I don't see a conflicting thing, I know that most of the network has been working on my chain. I don't know what you've done in secret, but assuming you don't have more than 50% of the compute power, you cannot.
And what if I'm red and someone just added in a request to send money that I didn't do, and suddenly I've lost.
So
I've given money to blue, and I don't even know.
Yeah, so this is actually signed by your own digital signature. Nobody can forge this. So miners cannot move your money unless a signature, the red guy's signature is here. Okay? Yeah.
Does anyone in the world have information required to know exactly the next hash, or like?
No, this is the reason it's called a cryptographic hash is because if I give you a hash, I tell you reconstruct any block, anything that has that hash, any message of any length, whatever you want. Even if you have a message with that hash, reconstruct another one with that hash, you will not succeed. Okay, it's considered hard, computationally hard.
Yeah, but even Satoshi Nakamoto can.
No, nobody. I mean, as long as hash functions are secure.
Yes.
And if hash functions break, then worse things happen than just Bitcoin collapsing. Like banking systems are not secure anymore. Okay. So let me get to the incentives. I'm running out of time. See, I told you that introducing the protocol takes a while. So this is mining, basically. You get to create the block because you happened to find the right nonce that computes a good block. And now we pay you for it. So the miner is allowed to include a single transaction that gives him money without a source, in some sense. And the money that goes in there is a little bit of fees from each one of these transactions. So they pay fees. And money is created out of thin air, newly minted coins, and we give it to them. And the amount of money that they can create is limited by the protocol. It is not allowed to just arbitrarily add money to his account. There's a fixed rate schedule that tells how much money he's allowed to give himself that was created. Again, all of this, once the block is sent to someone else, all of this is checked. So you can't just take fees that aren't yours. You can't put transactions that are not signed. You can't do anything that doesn't work. Everybody checks the signatures. Everybody checks the balances. Everything's checked. Okay, so now I need you to understand the amount of money that goes through, right? I think Bitcoin mining currently gives you about 6 Bitcoins in rewards every 10 minutes or so, without fees, right? The fees are also important, but slightly less. So 6 Bitcoin, a Bitcoin is now worth something like $60,000. I'm not sure about the, like a month ago. I'm not up to date. So 6 times 60,000, $360,000 are given out every 10 minutes to a computer that finds, a nice string of bits. And you can download this software, put it on your machine, and run and play with this yourself. Okay?
This suggests that if the value of Bitcoin falls below some threshold, the whole system will fall apart.
Yes, exactly. That's true. So the system really strongly relies on there being economic activity inside to fund what is essentially its security. Right? If the value of the coin is high, whatever you pay to the miners, they will be really appreciated, and they will be working, hopefully most of them are incentivized to work correctly, and we are robust against attackers. If the money becomes worthless, the coin plummets, the security of Bitcoin also plummets with it. Okay, it's bootstrapping in some sense, and it's of course very risky.
But how did they get value in the first place from the system?
It started with very low value,
why
but
was
then
it-
attackers also didn't have a very high incentive to attack the system, in some sense.
But why did anyone want to create a new block when the value was low?
So at first, so Bitcoin did something very clever. They were giving out a lot more coins, and the rate of coins that they give decreases exponentially. It might be too fast, actually. They started giving 50 coins per block. At the time, this was very little money. But what we're going to talk about next is mining equilibria. If this doesn't give you a lot of money, there's also not going to be a lot of competition to get that block, right? If, let's say, you get $5 out of it, you're not going to pay for like a whole data center of computers. You're probably going to run it on your machine at home and forget about it. So if this pays little, there's little competition, and then you can still turn a profit. The equilibrium would be of low investment by everybody. If it pays a lot, it will be a high investment equilibrium, but that will make the system more secure. Okay? So this is definitely a point to think about. Okay, so now I will mention this. This is the one slide saying there's a transition from proof of work to proof of stake systems. Instead of just proving that you've done a lot of computation, right? People understood that you're wasting a lot of compute resources, a lot of electricity, and there's a different way of using the system's own currency that you deposit inside the system as kind of collateral, or you can think of it, or like a resource that you expend, right? You lock up funds, and that allows you to participate in the protocol instead of wasting electricity. And I won't get into how to do that. That took a good few years to develop protocols that do this and are secure. Okay, because it's you're doing something within the system to stop it from being manipulated, and that's really dangerous. Okay, so now I want to step back from the protocol for a moment. I want to talk about the way computer scientists design protocols, and I want to show you that we violated a very important rule that we usually keep when we design systems. We think of protocols usually in layers. Like we have the internet, we're thinking of networking. And networking is usually something that we assume, right? Once we assume messages are going to get from computer to computer, we can go ahead and design a consensus protocol that uses networking. And this layer doesn't care what's running on top of it, and it doesn't try to interfere with messages based on what's running on top of it. And on top of our consensus protocol, what we've basically done is we sequence data, right? The people who are adding transactions to blocks are basically just deciding on their order in some sense. And we later take this sequence data and we interpret it either as native currency, right? We think of it as actions that we gave, commands that we gave to the bank to move money around. An alternative interpretation that we'll see tomorrow is to think of it as computer programs that are running and commands to computer programs. And then we build on top of that like more stuff, like you may have heard of NFTs and other tokens and other decentralized exchanges. We'll see all that tomorrow. And the problem is that, right, this guy running the consensus protocol can affect the sequencing data if he's, not oblivious to what messages he's sequencing. And that can affect, this layer of currency and smart contract. And that actually means affecting money. And in some sense, we also broke this layer model by saying, the guys who do consensus are actually going to get paid by the currency that they're using, that they're building themselves, right? So this is a violation of the layer model. We're allowing like higher layers to affect lower ones. And this is a recipe for trouble. And it actually causes, these fractures or breaks in the protocol that I'm going to talk about. Okay, so this is today I'm going to talk about, maybe this effect, how consensus is kind of broken by these incentives that you can change, and maybe later we're going to talk about this, how the fact that you're doing consensus in sequencing, you can affect what's running on top of it. So this is like a zoomed out overview of what's going to happen. So let me start like very simple. Okay, let's start with mining equilibria. And now we understood that we're going to get a lot of money if we, download this software and start mining. So maybe we should think of investing. And I want to, before I go to miners, I want to talk about like the, a very simple economic paradigm of what happens when you try to buy stuff, right? So let's consider a story of two falafel vendors, Alice and Bob. Okay, and Alice, has lower costs to produce a unit of falafel than Bob, and so they're very competitive. They set a price. Maybe their falafel shops are next to each other, and each one turns a profit per unit of falafel. And we expect, under some, naive model, that price dynamics will probably lead them to compete, and maybe, prices decrease, kind of like to the second price in some sense. And what we hope is that, if Alice sets her price to be exactly Bob's cost, then she can push him out of the market. She sells all the falafels. He's not there. He's not participating. And she becomes monopolist, but if he ever raises the price, he's going to come back, right? Something like that. So this is what we'd expect from falafel, okay? Under some setting. So now I want to ask, what about miners? Okay, we are going to have people who are more efficient and less efficient at mining. So this is actually an insight from a much more detailed paper about equilibria, right? I'm kind of distilling like one of the basic insights from a paper by Amos Fiat, Anna Karlin, Elias Kotsoupias, and Christos Papadimitriou, just to show you that this is not trivial. So now I'm going to write the utility models of two miners. And I'm assuming they're the only two participants in the system. So each one of them gets to pick, right, there's a block reward that they get. They get some fraction of it. We'll talk about that in a second. And they have a cost of electricity. And their decision, the decision of the miner, is how much hash rate to invest, right? How many machines do I invest? And the more I do this, the cost increases because I pay more for electricity, but I also get more of the block reward. So we know from the mining procedure that if I invest H1 hash rate and the other invests H2, I get my relative share of the block rewards. So if I'm an alpha fraction of the blocks of the computational power, I will get an alpha fraction of the rewards. Okay, so this is why this utility function is here, and you have the same one, but in reverse with H2 here. So this is like the most simplified model for what it costs to mine, and you can easily think of more complicated ones. But even here, it's already interesting. And here's a claim that goes against what we saw with the falafel vendors. H2 equals 0, right? The second most efficient miner, not mining, is never in equilibrium. He's always participating in the game. So we never push him out of the market in equilibrium. So let's see why. I promised everything will be trivial, so I'll just show you. Right, H2 equals 0, what does that mean? We can strike that out here, right, that's gone. So H1 over H1, then that's 1, so we can just erase that. Now, what is the best response of Alice as the most efficient miner? If she wants to maximize her utility, she sets H1 to 0, right? So H1 has to be 0. If H1 and H2 are 0, right, that's the consequence, right? In any equilibrium in which H2 is 0, H1 is also 0. So Bob can, of course, defect. And he can come back and invest a little bit of mining power and get all of the blocks because he's going to have, right, his fraction of blocks will be everything. Right, so that's obviously not an equilibrium. And you can actually compute what the equilibrium is. And it's an interesting result from that paper that the equilibrium of any number of miners, not just two, the two most efficient miners are always mine and always have a profit, regardless of efficiencies. And other less efficient miners are sometimes also mining as well. There are conditions for which it happens. So this is already not intuitive. It's a very good thing that this happens because if you remember, if we have an attacker, anyone that controls more than 50% of the Bitcoin blockchain, we're in a heap of trouble, right? If there was only one large miner taking care of all mining, we'd be in trouble. This guy is already controlling the Bitcoin blockchain on his own. So in some sense, it's a good thing that this happened. And less efficient ones can also mine. Any questions? Yeah.
And the equilibrium should be mixed strategy?
No, the equilibrium is pure, right? If you think about this, the H1 is like a continuous function. This is right. This is the existence of an equilibrium is just because of the compactness of the strategy space, and whatever. All the conditions are there. Everything is smooth. Everything is differentiable. Everything is nice. Yeah.
You assume that if you're a monopolist, if Alice is alone, she can get blocks without investing any effort. But that's not the Bitcoin rules. Even if you're alone in the field, you must invest a certain amount of effort.
So that's not true, because what happens is the amount of if the mining takes too much, right? If you remember, we adjust the difficulty of the mining to create a block every 10 minutes. So if Bob drops out, mining readjusts and becomes easier. Okay? A block will be created every 10 minutes in expectation, and we will adjust difficulty. So that means if Bob drops out and Alice remains there with some mining power, the protocol will make it easier and easier and easier to mine. Okay, so that's an interesting observation. So the reason for this is because of the difficulty adjustment. And the reason for the difficulty adjustment, by the way, the reason a block is created every 10 minutes is for other security reasons. If blocks are delayed too long, the security of Bitcoin can be shown to drop off a cliff, basically. Right? So Bitcoin delays blocks to be created every 10 minutes. That's a lot of time on purpose. And they regulate this rate and try to stick to it via algorithmic means. So this is why we're not looking at the absolute values of H1. Right? This is if everybody's hash rate just increases by a factor of 2, they're still winning the same amount of rewards, because the difficulty just goes up by a factor of 2. Yeah.
Is there a single equilibrium?
Yes, in this case I think there is.
In case of 2.
Right, this is again because of compactness and so on.
And second question is, are the hash rates proportional to inverse costs? Then?
Proportional?
Like how? Like is your if you pay less, is your hash rates higher in equilibrium?
If you're less efficient, your hash rate is higher. Yeah, they are, but not proportionally. There's a little bit that depends on the other miners.
Right.
I didn't put in a slide. I have a slide for like the equilibrium solution. I didn't put it in because of lack of time. But I urge you to see the paper. What I want to say is this is already simplification that we're going to look at from a different direction. I assumed a constant investment over time. That's all right. This is a temporal game. We're running this over many rounds in some sense, and many blocks. We're going to see that this assumption of even constant investment is wrong, just wrong. Right, so now I want to show you the second part, that deviations from the Bitcoin protocol are actually profitable. Okay, so the protocol itself is not an equilibrium, right? We thought about the mining equilibria. Protocol itself is going to break, and I'm going to show you several ways in which it's not an equilibrium that are going to kind of maybe probably disturb you. They disturb me anyway. It seems that miners can make more money by not following the protocol, which is always bad. So let's start like with the simplest model. Let's just recap what we know, right? Blocks are created, let's say IID, by either the attacker with probability alpha, or by an honest node with probability 1 minus alpha. This is basically their fraction of the hash rate. And each block just specifies a single parent. There's a question here.
Yeah, going back to the previous
Okay,
slide,
okay, yeah.
where's the protocol stored and how do we know it can't be changed?
Sorry?
How do we know the protocol can't be changed and where is it stored?
The protocol is basically stored on many machines out there, right? And let's say one of them decides to change. Okay, so whatever messages it outputs are judged by code that's running on everybody else's computers. So it's an equilibrium in some sense of what's out there. And so some protocol changes, might not hurt you, right? You change some stuff, the others still accept your messages. And some that do hurt you. I mean, if you decide to say, I create more money in every transaction, in every block, I give myself more money, others will just reject your message. And so you're outside of the game now. But if you say something like, when I create a block, I delay it, I keep it to myself for 5 seconds, and then I release it, that's a deviation that doesn't disrupt you, but in that sense, you could make a profit, and this is what I'm going to show you. I'm going to show you that there are deviations from the protocol that I do on my own without coordination with others, unilateral deviations in the sense of equilibria, right? And that I profit from, okay? So our model was, right, we have these blocks that, and I'm going to denote honest or attacker blocks with H and A, depending on who created it. And it's not necessarily a single honest participant, it could be a lot of honest participants, but they have together a mining rate of maybe 1 minus alpha, and each one specifies a single parent. So actually what we get is not a chain, it's a tree with some of these branches dying off as nobody tries to extend them. And our game is that we're only paying the blocks that are on the longest chain, right? That's the person who gets money they can write a transaction here that pays them money, but if you created a block which did not end up on the chain and you gave yourself money, that's not in the history of transactions, so you didn't win money. Okay? So you only get paid if you're on the longest chain and not if you're not. And now, right, what's honest behavior? We talked about this already. You mine only on the longest chain, you extend only the longest chain, right, and you maybe break ties in favor of the earliest block received if there are chains of equal length. And you publish blocks immediately. That's one of our rules for the protocol. So this is honest behavior. And now I want to show what can an attacker do. So an attacker can mine anywhere. For example, if this was the longest chain, they can extend this chain instead if they want. That's fine. They can publish blocks with delay. So maybe I denote here a block with a dashed line if the attacker created it but kept it from everybody else. So it's a secret block that was mined. So an attacker can create a block and not tell everybody else. He might have a longer chain, but not tell anybody. That's fine. And now, before I answer that question, what do we wish to maximize? So I'm going to argue, and this is a bit contentious, or at least you wouldn't agree immediately, you wouldn't see why this is correct immediately. He wants to maximize the fraction of his blocks on the chain, on the main chain, out of the total blocks on the chain. Okay, so it's not doesn't look like absolute profit, it looks like relative, but this translates to absolute profit. Why? Because Bitcoin modifies the difficulty so that the blockchain, the main chain, creates a block every 10 minutes. So if you manage to get a higher fraction of blocks on chain, even though some of them fall off the chain, doesn't matter. Your fraction of the blocks will end up being a higher fraction of the overall reward, which the protocol makes sure is constant over time.
This assumes risk neutrality.
This assumes risk neutrality.
This is like large sums of money.
We'll talk about risk later. Risk is very important. Yeah.
How do you know that you're on the longest chain?
How do you know that you're on the longest chain? You don't know up until much later, when you eventually, when the chain is 1,000 blocks longer than whatever you have, it's unlikely that it will ever get replaced because it's really hard work and so on. So there's no moment at which you really know that you're on the longest chain. It just becomes more and more likely, right?
So you can't actually check. There's no registry to check against.
No, but what I'm saying is eventually we're going to judge the outcome of your behavior, right? You're going to pick a strategy as an attacker. The honest nodes have picked their strategy, and we have a probabilistic process of blocks getting created, and we're going to see what you expect to get, right? So that's going to. So this model, by the way, is due to Itai Eyal and Emin Gunsirer, which showed the first deviation. And before them, of course, there was a paper that showed that Bitcoin protocol is actually in equilibrium, which obviously they stepped out of that paper's model by allowing you to publish blocks with delay. And that showed that it was not. Yeah.
The blockchain creation is independent of whether or not any transactions are happening.
Yes, the blocks could be empty. Right? For our simplified model, I'm even thinking of these payments as like constant. These are just the block rewards. And there are transaction rewards inside there, but for the purpose of this discussion, I'm ignoring any variations in pricing here and in rewards. I'm just going to think of this as 1 unit reward per block. Okay, for now.
What's the incentive to create blocks? I mean, okay, you get
You
6
get paid.
Bitcoins, but then if nobody is transacting and you keep giving your computer.
No, this is, of course I'm assuming people are transacting here, but let's assume whatever they pay as fees is already in here. It's within this reward. It's together. But what I want to show you that even this case where the reward is just fixed and everything is simple is not, I will deviate from the protocol. Of course it will happen even more severely if these rewards are somehow varying and so on. So even under the simplified model, you will deviate. Okay, so this is usually where I get the most arguments from the audience. So this is a consequence of the need to regulate the pace of the blocks being created. Okay, so Eyal and Sirer actually suggest a strategy. They call it, I call it SM1, selfish mining 1, because there were others that followed. They just called it selfish mining. And in their strategy, the attacker tries to create a block, and when it succeeds, it keeps the block secret. It doesn't tell anyone. And then one of two things can happen. One, the bad thing for the attacker is that the network will build a block and maybe another one, and now the network has a longer chain than the attacker. So the attacker, in this case, abandons this block and tries to mine again here. Okay, and you give up if the honest chain is longer. And so you might again succeed in mining a block, keep it secret. But the good thing that might happen, this happens occasionally with some probability, is that the attacker creates another block before the network does. And then what can happen is that if the honest network creates a block, you can tell the world about your blocks, and you override the chain, and you make the honest guys lose a block. And these suddenly are in the chain and get paid, and mining will continue here. Okay, and this also happens, right? You could have 2, 3 blocks, and 4 blocks, and 5 blocks, and so on. So for any length, you're basically keeping them secret until the last minute when the honest chain is almost caught up to you, and then you try to destroy as many honest blocks as you can. Okay, yeah.
So here, do you have to wait 10 minutes before publishing the second A block?
No, you can do this like a second after, because 10 minutes is not really the time between blocks, because the time between blocks is in expectation 10 minutes.
I know, but even that, I would expect the variance not to be like 9 minutes, 59 seconds.
Yeah, but the protocol doesn't check. If you start putting checks into the protocol, we have to analyze the changed protocol. Current protocol doesn't do this.
Also, why cannot you use the previously mined A?
Because it contains the hash of this block inside it.
So they are different.
And you can't change it, because otherwise the nonce and the entire cryptographic hash of this thing would change. So you can't reuse old stuff. This is an important part of the security of the blockchain, by the way. That the attacker that mined maybe 10 years ago cannot, pull out a block from the past and use it now. Yeah.
In this scenario, the attacker could have both these blocks be honest.
No, that's right. So, of course, we have to compare to mining honestly. And it looks like this is a very dumb idea, right? Because the honest network has more computational power than the attacker. So usually, we'll expect to see this happen more than we see this happen, right? But that's more likely. And he loses money here, right? A lot of time.
But he does not gain money otherwise.
Right. So this is the surprising part of this. When you analyze this exactly, right? And the hint is that here he only loses a single block every time they overcome it. But here, when he overcomes them once, sometimes they lose a block, sometimes it's more. So there's a tail here. There's a probability he gives the attack if they might lose 2 blocks, 3 blocks, 4 blocks. When you do the analysis carefully enough, you see that the fraction of blocks that end up on the longest chain can actually increase. Let me show you the exact result. This is not in a formula, but okay. So this is the hash rate of the attacker. The dashed red line is what happens if you mine honestly. So if you have like a 25% hash rate, you get 25% of the rewards. So this is just a straight line with a slope. And The strategy of Eyal and Sirer is plotted here in blue. So for low hash rates, you're actually losing money if you follow it. Most of the time, you waste your blocks. When you pass 33% hash rate, you start making money. Okay? And the reason I show you this plot is that we had a follow-up paper that analyzed this and showed that there are even better strategies. You see them here in circles and X's that make even more money than SM1 and slightly more. Sorry? Percent of all rewards. You know, if you look at a long enough chain, right, I got some fraction of the rewards. As the attacker, the honest guy got some fraction of the rewards. And what this actually says is that if I'm here, I get more than my fair share of rewards. I have maybe 35% of the hash rate, but I'm getting maybe 40% of the rewards.
So you need huge part of the huge fraction in order to get something.
So this model actually is when you have no delay in the network. Every block arrives instantly to its destination. And one of the results that we also show in the paper is that when you have delay in block mining, even here you have strategies that do better than honest mining. Hash rates, arbitrarily low hash rates. But of course the profit is very small, but you could do better than the protocol. Yeah. Of course, because one of the things that happens is that the chain doesn't grow as fast. You have an adversary that creates these long chains that look like double spending attacks, if you remember, right? And occasionally sends them out to destroy everything on the blockchain, right? That looks like a double spending attack, and he's actually making money while doing this double spending attack constantly. So this is very bad. And the worst thing is, this is a unilateral deviation, right? An attacker deviates. So what would be the best response to this deviation, right? The protocol, if somebody started doing this, everybody else would react, right? And so we don't know what the protocol would be because we don't know what the equilibrium is. But the current protocol is not an equilibrium. Yeah.
I'm kind of confused how the attacker makes money. Is it by somehow manipulating the trades themselves? Or because it seems like it could have equally added 2 honest blocks and received the same rewards as adding 2 attacker blocks.
Yes, but what happens here is that he's going to get, let's look at it from a different perspective. Let's say this didn't happen for a moment, right? Forget that. So we have to do the analysis more carefully. So he could have added 2 honest blocks, so 2 attacker blocks, and he would have gotten 2 block rewards. But the time between block rewards here would have been 10 minutes.
Oh.
But here, because he destroys this and he does this repeatedly over time statistically, the blockchain is going to slightly speed up. So these 2 are going to be a larger fraction of the rewards. This is going to happen for him more and more often. Basically, the entire process speeds up, and he gets more blocks per second inside the main chain. Okay? Yeah.
What would be the best response to this attack?
We don't, right? We know how to compute the strongest attack. This is the thing, the results from our paper. We reduce it to like solving a series of MVPs and so on. And this was useful because a lot of people offered suggested fixes to the Bitcoin protocol that would make it in equilibrium. Of course, when you fix the protocol, the attack just happens somewhere else. Usually, the best attack changes, and so you could compute an optimal attack against the change and show that sometimes the suggested fixes actually made things worse in terms of the best response to the fix. But we don't have an answer to this yet. At the moment, there's no protocol that's in equilibrium, or there's no equilibrium for this protocol that's known. Part of the paper by Amos Fiat, Carlin, and so on, looks at equilibria over temporal, but without these games of delaying block creation and so on. So they look at equilibria in different sets. Yeah.
Can you empirically detect that this is happening?
Yeah, you will see a lot of these overrides happening, and we don't see them.
You do not see them
The
data. So
you do
it's
not see them.
happening?
You do not see them. They're not happening.
So how do you explain that?
We don't. We don't know.
There's money on the table.
No, I'll get to that if I have. I probably won't have time for a lot.
You said that it's 40% of
Yeah,
hash
yeah,
rate.
yeah.
No, but
So-
he says that with
so,
network
I'll give you the headline,
you
okay?
have a little bit of-
The headline is, miners who are large enough to do this have a stake in the system operating
No, but
well
you
over
said
long
that,
periods of time.
You said that with delays it can happen even if you're tiny.
Yes, but very small gains for delays. I don't really believe that somebody would go in and change it for small delays. So I will give you a teaser for later. I will show you a deviation that people actually do, that we saw that they do. Which was surprising because you expect incentives to motivate people, right? That's the definition of incentives. They motivate people for action. Every model that we have shows we have a lot of attacks on the Bitcoin protocol. None of them have been observed, and we have one that we have seen.
Maybe restoration.
I think it's long-term thinking. So this gives you money here, right? Here and now, or in the span of a few weeks. But then this erodes confidence in the Bitcoin system. It means all your investment in hardware is going to go to trash. The value of the Bitcoins that you mine will decrease because people are running attacks. The protocol destabilizes. So the large actors have, in some sense, an incentive to play nicely. Maybe the deviation that I will show you is under the bar for being okay, because actually it wasn't detected for 2 years. People were doing it for 2 years before we found it. And then they admitted doing it, so we know that it was done.
When
Yeah.
small attackers do, is it just harder to detect that they're doing because it's like such a small thing?
Yeah, it's a small. I don't think it's worth the trouble of them changing code. There's more risk that if you change the code, you will mess up and lose your money, right? You'll introduce a bug, and if you lose a block, right, you lost $360,000 by a glitch in software. That's not nice, and it happens. Yeah, I'll get to everybody.
Is it possible that the people who are trying to attack are just not aware, or is this too late?
No, they're very aware of this. This is a very famous result by now. Yeah.
What would happen if you were to combine like attacks with, because this is a deviation with a mining protocol where you're only assuming you have profit from your payment from mining. But once you're overriding chains, you could also attack.
You could also attack. People have looked at this. Of course, it makes it even worse. Yeah.
Is one big unanimous mining tool in equilibrium?
No.
No?
No, because in the sense that it takes over all of the network's activity, it can decide not to publish some transactions, it can censor. When this happens, everybody freaks out. So, so it's not it's an equilibrium in maybe some model, but it's not an equilibrium in real life in the sense that everybody freaks out and stops using Bitcoin, right? And this almost happened a few times in the past.
Long time ago, or?
A long time ago, maybe. But I think most mining tools, if they become too large, they're careful about it, and maybe they split into some entities because they understand the public perception of this would be really bad. Let me continue. I have more interesting stuff. So I want to show you a different insight from the same paper by Fiat, Karlin, Koutsopias, Papadimitriou, and another paper by Goren and Spiegelman. And this is that even the amount of hashing that you do over time shouldn't be fixed. Okay, so let's talk about the difficulty adjustment mechanism for a moment because it's really important, right? So this is built in the following way. If this is time, and this is the hash rate. So let's assume Alice and Bob here each operate one machine, right? One mining machine, and they're mining. And so there's a period of 2016 blocks that is supposed to take, if you do 10 minutes per block for 2016 blocks, it's exactly 2 weeks. It takes 2 weeks. And if they mined at this pace and it actually took 2 weeks, then difficulty doesn't change. So when they mine again, the next epoch is expected to take 2 weeks. But let's suppose Bob suddenly buys more mining power. Right? So now he doubled the total mining power. Used to be 2, now it's 4. So we compute hashes at a faster pace. So here, this was at the end of the epoch. So the difficulty was set when he did this. So now he can mine twice as fast. He finds blocks twice as fast. So he mines 2016 blocks actually in 1 week. The mining power, the hash rate grew by a factor of 2. And the epoch took only 1 week, but we gave out the same reward for 2016 blocks. So we gave it up much faster. So now the end of the epoch arrives. We see that we mined 2016 blocks in 1 week instead of 2. So the Bitcoin protocol reacts to this by doubling the difficulty. It always tries to make the previous epoch lasts 2 weeks. Of course, it has passed, it's already gone, but we adjust the difficulty so that the previous epoch would last 2 weeks. And so if Bob and Alice continue mining with this increased rate, it will again take 2 weeks. 2016 blocks will be mined. Okay? So this is the dynamics. Now let's consider 2 different behaviors, right? One behavior is just the regular one. You know, Alice and Bob are mining at the same rate. Nothing changes. Every epoch takes 2 weeks. And we'll think about their rewards. In the second scenario, I'm just going to equip Bob with the wonderful technology of an on-off switch. Okay, you can just turn off all of these computers. It doesn't do anything except turn them off. So let's assume before that he was mining along with Alice for 2 weeks. So the difficulty is set for whatever. Then he turns off his machine. So what happens? How long will the epoch take? 4 weeks, right? So 2016 blocks are distributed over 4 weeks. And what happens to the difficulty? It decreases by half. But now, because it's really easy, he turns his machine back on. So how long will the next epoch be? It's not going to be 2 weeks. If he kept mining at the same rate, it would be 2 weeks. But now he doubles the hash rate again in the system, so it's going to run for 1 week. And then this again triggers a change of difficulty back to the original difficulty, but he turns off his machine, and again it takes 4 weeks, and again 1 week, right? So we can repeat this. What I want you to notice is that we actually did 4 epochs when previously we did 5. And Bob was, turning, he wasn't participating here, so he doesn't get rewards, but he also doesn't pay for electricity. And here he was participating, he pays for electricity and gets rewards, and you can repeat this forever, right? As long as Alice is not reacting, we're thinking of a deviation here, not something more clever. Now let's I'm just going to give a numeric example, right? I'm going to ignore this part where they were both mining at the same pace, and just look at the whatever repeats, this repeating sequence. So we have 10 weeks here that have been run with 2 different strategies. Okay, so let's assume for a moment that I denote by R not the reward for a single block, but for 1,008 blocks. Okay, so this is basically during an epoch we have twice that, but this is like the weekly rewards that are being distributed, and this is the cost of the electricity cost of a single miner of Bob for 1 week. Okay, so Bob's electricity cost would be this. So it's slightly below 1/2, a little bit. And of course I can set up equilibria so that this will be the case. And now here, let's think of his reward. He was getting half of the weekly reward because he was splitting it with Alice for 10 weeks. And he was paying his electric bill every week for 10 weeks. Okay, so he basically made 1/16 every week of reward over 10 weeks. So his total reward is 10/16R. Okay? And here what happens, he doesn't pay anything and doesn't get anything for these long epochs, but he does gain rewards here. So what I claim is that for these 2 weeks, we gave out 2R rewards, right? Because we gave 2016 blocks reward here, and R is 1008. So we gave twice that, but he got half of that because he's splitting it with Alice. So for every week here he gets 1R reward, but we had it for 2 weeks, here and here. And he paid his electric bill only for 2 weeks, here and here. Okay, so that's 7/16 of R, whatever. And so, right, if you look at this, he gets 2R rewards and pays 14/16R in payments, so he gets 18/16 reward, which is more than what he had here. So now this is a little weird. Bob has a deviating strategy of just turning on and turning off this switch. It's not sophisticated. He's not hiding blocks. It's not like go into your code and do something fancy. Now, I will say the caveat here is that he's a fairly large miner, right? He's in this example, he's like half the network. But Goren and Spiegelman showed that there's a large region in which you will actually deviate from just constant mining rate. And this already means that Alice, needs to react to this And so the nice thing in these papers that I'm just distilling these essence of ideas from is that they think about the temporal equilibria, and it's not constant investment. Okay, constant investment is not equilibria in many regimes. So this is bad for the protocol as well.
Why is it bad for the
Yeah.
Why is it bad?
Why is it bad? Because first of all, this is really bad because now, if you think about it, Alice here is paying her electric bill and not getting rewards. It's not profitable for her to mine. So what will she do? She'll probably jump off the protocol as well. And then we might grind to a halt. This is the worst thing. What makes it even worse is that Bob doesn't have to just turn on and off his machine. During these 4 weeks, he could actually use his machines to mine a different cryptocurrency. So he can make even more profit. And he's oscillating between that cryptocurrency, so the same effect is happening there because he's turning on and off mining power in other places. So everything is going to go nuts if this happens. You can't depend on when the next block will appear. Everything is going to be really bad.
Transactions slow down.
Transactions slow down here over the capacity of the blockchain. Fees will go haywire.
Do you see this in data?
We saw it in practice when Bitcoin Cash showed up as a fork of Bitcoin. People were hopping back and forth. The thing that helped is that Bitcoin Cash changed their difficulty adjustment protocol, not to operate in epochs of 2 weeks, but to be more instantaneous, and so the oscillations vanished. But Bitcoin still does this, so you could still, at the very least, you could switch to mining Bitcoin Cash, where oscillations maybe don't happen. Bitcoin still will oscillate.
But maybe the fact that this is not an equilibrium is good news. It means that we should not see this in practice so often.
So this is something that we think we can fix more easily compared to the previous problem, because changing the difficulty adjustment algorithm to be something more continuous. So Bitcoin Cash does it, and Ethereum did it. Basically, you readjust the difficulty every block instead of every epoch or something. But it's not clear that you don't have deviations there as well. Nobody analyzed that sufficiently well, right? So this is already like an interesting result that was found. Let me give you another aspect of this. When we saw this, we noticed that you're also stretching time in the protocol. So we had the number of blocks that was created here is I think 80% of what happened here. So time, basically, if you look at block creation rate, flows slowly here. And then we noticed that in Ethereum, you have, if you were doing this in Ethereum, you actually have systems that you could deposit money and you get interest rates. You get interest from them. So there's a platform called Aave where if you deposit money, you get paid based on time. They look at the clock and not at the number of blocks. There's a different platform in Ethereum where you can acquire interest over blocks instead of time. They use a clock, which is the number of blocks. And then we said, okay, we have a different attack that slows down Ethereum, by the way. And then we said, okay, we can kind of connect those. We take a loan from one of them, if we want. We deposit in the other. And then we slow down time, the block rate. So we actually end up paying less interest per block. We take a fixed rate interest loan, in some sense, and we deposit it in the other platform. And then we get interest based on time, but we pay interest based on a slower block rate. And we can make money. Okay? So weird things happen. Right? This is a way of us intervening with the mining to change something at the higher layers because they were doing calculations of time differently.
But Ethereum currently is proof of stake. You cannot do it.
Right, so this was for the old Ethereum. We could stretch and squeeze the time based on different mechanisms that allowed for difficulty adjustment in Ethereum. Now Ethereum is proof of stake. I'm not sure that you cannot change the block rate even now. There's like no proof that that doesn't happen. Like maybe you could stretch and squeeze time. I wouldn't say it's impossible. Nobody tried so far. Okay. So the question that you asked. Why don't we see stuff for strategic mining? And I gave you this speculation that people are thinking of their long-term incentives and they want to behave by the rules. It's very easy to detect deviations. And then, of course, we found a way to deviate where we found evidence. So this was in the old Ethereum before it was proof of stake. We actually looked at the...
Is there a method to punish deviations that are detectable?
I think the social interaction would punish them. The developers would change stuff, and or the protocol would be shifted in a way to stop deviation. When the selfish mining paper came out, the Bitcoin people were actively threatening. They said, if we see that miners are doing this, we will react by changing the protocol in a way that you will not be happy with. So one thing that they can do is, like, if they shift the hash function, they destroy the investment of all the miners in their hardware. Right? They pretty much erase its value. So they have like a doomsday device that they can activate if that kind of an atomic bomb to destroy all of the miners' worth. So there were times when they were threatening each other with other things as well. So this is from the Ethereum yellow paper. It's a specification of the Ethereum protocol. And we saw this weird formula for changing the difficulty of a block. So this is the difficulty of a block based on the difficulty of the previous one. There was some stuff here. And we read the paper, and there was this ambiguous line. And it said, a smaller period between the last two blocks results in an increase in the difficulty level. So if the last two blocks took too long to mine between them, that means the difficulty should increase. And I had two students who were kind of debating what this line means. There are two options. I'm working on this block. I'm trying to mine it right now. And these are the previous two blocks. So does this mean that I'm looking at this difference in time between the last two blocks that were mined successfully? Or am I looking at the block that I'm currently mining compared to the previous one? And the reasonable thing to do, and we're betting this is the case, is to look at this gap. Okay, so the way to settle this argument when the wording is ambiguous is to go to the code, to open the function. And so we went to see what Ethereum actually does, and they're actually looking at this gap in time. So that means, so what this t that goes into this formula is the difference in time between the block I'm currently mining and the previous one. And so you see that there's a rounding down mechanism for in increments of 9 seconds for some reason, right? So this is the mechanism. And if there's, I don't know, 100 seconds have passed since we successfully mined the block, what this would do is it would make the difficulty lower. This is, here's the negative. We take 100, we divide by 9, we round down to the nearest integer. And that implies a decrease of difficulty by a factor of, maybe something times 1 over 2048. So a tiny decrease in difficulty would occur over time. So we said, okay, probably the time, what does it mean to have the time between this block and this block? We can write whatever time we want here. We can put, nobody knows what the clock on my computer says. Maybe it's a second off and so on. So there's a mechanism, Ethereum blocks will not be accepted if they're like 2 years into the future. They're going to be thrown out, or if they're too much into the past. But, and actually the time has to be monotonically increasing. So, but we can fudge the number, like we can shave a second off if we want. And then here's the attack. Okay, so what do we do? So let's suppose a good guy and a bad guy both mine a block 9 seconds after the previous one. Okay? So 2 blocks appear. 9 seconds and 9 seconds. One of them says the correct time, 9 seconds. The other one lies and said, I actually mined 8 seconds after the previous block. Okay, who's going to know? And then somebody mines the next block, and it's supposed to pick which one of them does he point to. So what does the rule say? The chains are equal length, but I kind of lied to you. The protocol doesn't say choose the longest chain. It's choose the highest difficulty chain. The longest chain is usually the one with the highest difficulty. When you have 2 chains of the same length, but here the difficulty is slightly higher because the time between blocks was too short. And this is under this rounding down of 9 seconds. So the difficulty here is slightly harder by a factor of 1 over 2048. You know, we add you know, less than a tenth of a percent of difficulty. And so this block would just point here. And in Ethereum, they actually paid blocks that are off-chain some small amount as well. But the reward for the block that is on-chain is always larger. And so you want to lie and shorten your timestamp by 1 second. And it does make your blocks less likely to be created in the first place, but more likely to win if there is a competitor that would take away most of your money.
Can't you just take the timestamp from another source, not from your...
That would mean I have to trust that source. That brings a world of security problems at your doorstep. Time is relative in these things, because every time I say time is something, by the time the message gets to another computer, I don't know how much time has passed, how long was the message delayed. So there are clock synchronization protocols as well in distributed computing. So you claim earlier rather than later, which would be my first intuition, right?
Why
to
can't
make
we-
the block easier to mine.
Why can it be worse to declare early?
Why can it be worse? Let's say there are never conflicts. Like if communication is really fast, then I'm never in this block race with someone, and I just made mining a little harder for myself.
For the next block?
For myself.
For yourself?
Yes, this is the point. This gap applies to the difficulty of this block.
Ah,
That's the weird, nonsensical part here. And so,
So I lose a bit here, but I get...
but I
the
get a
other
lot
shape.
more here by winning these block races.
But didn't you say that like you tie break in favor of what resources?
Yeah, but in case the difficulty is different,
Or then you first
then there's no
break?
tie breaking needed.
Okay.
Difficulty is first.
I see.
If difficulty is the same, I break ties. This is not a tie. That's what I'm saying. And so we went to look at the distribution of time between blocks, right? We looked at the Ethereum blockchain. We started at block 12 million or something, and we took a 500 days worth of statistics, and we saw this weird thing. It's supposed to be distributed exponentially, and it's okay that this column should be higher, but it's okay if it's lower because there's some delay in propagating messages, so you don't see blocks that show up 1 second after the previous one, as many as you would expect. But then we saw something funny here at 9 seconds, and something funny here at 18 seconds. And then we said, okay, this is for all miners. Let's look at every miner individually. And we found F2Pool. Here's the smoking gun, right? They never, in 2 years, never created a block that was 9 seconds after the preceding block. Not once. And never created a block that was 18 seconds after the preceding one, and never created one that was 27 seconds. And then we were like, oh my God, they're deviating from the protocol. At last, incentives affect the behavior of people. Who would have thought? Right? Because up until then, we didn't see much of that in Bitcoin. And then we tweeted this when we wrote the paper, and they admitted, because at the time, Ethereum already was on the verge of switching to proof of stake. So they said, oh yeah, we did it. And we calculated how much money they made. Right, so we actually found a bunch of other miners, smaller ones, that also did this deviation. They started about the same time.
I don't know who admitted it.
The people running F2Pool. There's a guy, like a CEO. He said, yeah, we were doing this.
It's hard to deny.
We found a hack. It's very hard to deny. These statistics, like everybody can access this
So
data.
did he, like,
It's
why
there.
did he admit? Did he take pride on this?
Of course. And they don't care. I mean, the mining business was basically shut down. Everything moved to proof of stake by that time. So any social consequences were gone. They just made money.
But presumably you weren't the first to discover this.
Well, they were first, obviously, to discover and implement. They thought about it first. They looked deeply. And
Right, but wouldn't
it
someone
wasn't
else-
known. No, it was not known. People were really surprised when we showed this.
So it's not published.
Not published. I mean, they're known to whoever was doing it. So we saw that more than one miner was doing it. They started slightly after F2Pool, but we don't know who these addresses are. We think they're also F2Pool. So if you remember, when a pool grows too large, that becomes risky. So they could be mining other identities as well. So we don't know. Maybe these are where they tested this.
How much money?
So the money, we actually looked at, you know, the victims of this crime, and you look at another pool, Ethermine, which is another big one, and you see that whenever they created a block, which was 9 seconds, this is the number of uncles they created. Uncles were off-chain blocks. So when they created a block that was 9 seconds after the predecessor, it had a higher probability of getting pushed off the chain because of this adverse behavior by their opponents. And so we calculated that the difference was, you know, tens of millions of dollars for just shaving this 1 second strategically off over 2 years, right? A lot of money. So nice to do, right? I'm out of time, I think. I'm not going to get to risk. Not tomorrow. Tomorrow we have other bigger fish to fry in some sense. I will say maybe one basic idea. We were looking at this utility function before of miners, right? I'll just give you the gist of this. There's the electricity cost here and the reward, sorry, electricity cost and reward. The reward is in bitcoins, and we always assume like you convert it to dollars if you want to think about what that does. But this really oscillates, you know, the exchange rate. And when I buy my machine, I buy it for like the next 2 years. It's going to be mining over 2 years. What's going to be the price of Bitcoin in 2 years? It's going to be wildly varying. So my investment is very, very risky. And the right way to think about Bitcoin mining machines is actually to use tools from finance, in my opinion, right? Because if you think of a Bitcoin mining machine, it's actually like an option. So what do you do when you have an option? You can decide, like in a year, right? You bought this machine. It allows you to convert electricity to Bitcoin in a year's time, and also, you know, every 10 minutes, right? And then you can decide to do it. But if the exchange rate of Bitcoin drops too low, you could turn off your machine and not pay the electricity price. So this is like the call price of an auction. Strike price, maybe the term. And so you could do option pricing theory on this. And when you compare this to the expected reward that people usually use, you see that this implies a very different price for Bitcoin mining machines. And maybe I'll just jump to the end, right? So actually, I don't know if you, this is probably separating the generations here. You get the meme? So miners are looking for a man in finance to, I don't know if you get the joke, to decide on how to price machines. And when we compare the two alternatives, you can actually, let me get to the last slide of this. This is how much I was hopeful that I'm going to make today. The last slide basically shows that this is the price of ASICs that you could find on the market for some mining machine. This is the cost of an imitating portfolio that you could construct in finance that we thought you should buy. This was the profits that you made with your ASIC if you were mining. We can kind of think about what it would cost you. And this is what the imitating portfolio would actually do. So you paid less and got more by using tools from finance. This actually graph actually shows that we're misinterpreting the way that Bitcoin mining is going to grow. So the fact that we're making more profit than expected shows that there's a gap in the model between model and reality here. Yeah.
If you can look at the investment as an option, you can look at the investment today and use implied price of the Bitcoin in the future. So what it is today.
Yes, and there's another like meta level. If you are a manufacturer of ASICs, your decisions on how many ASICs to manufacture today is an option on options in some sense.
Right.
It's highly leveraged, and you see what happens when the Bitcoin price goes up. ASIC manufacturers run out of hardware instantly, so they always overproduce a little bit because they expect that there might be a windfall. I mean, if the price goes up, they know they'll run out. They don't overproduce because they worry about what happens if it doesn't. And this happened to NVIDIA, by the way. They ran out of the GPU cards for mining Ethereum. At some point, the gaming world was left without GPU cards for gaming because Ethereum jumped up in price.
So hasn't anybody computed the number, the implied price of Bitcoin in the future?
So we've done some projections to do this, right? So both for the cost of a, so you're saying this can be flipped to see the cost of ASICs today as a thought of a,
as an option,
as an optional price. So no, that's not exactly correct, but because there is also you need to factor in what your prediction of technological growth for ASIC mining. So if ASIC mining improves in the future, that also changes. But you could factor that in. You could add this.
These are known parameters.
Yeah, so you could, I don't think somebody did it, but it might be interesting to do. Yeah.
Would you say that cryptocurrencies are parasites on the economy?
Are they parasites on the economy? No, I don't think they are parasites on the economy. They're, so we're out of time, right? I'm in overtime already. They exist. I mean, like other things, they have maybe side effects that we don't like cars pollute the environment, right? They have externalities. Bitcoin has its externalities. We can decide that we don't like Bitcoin, right? It's kind of like deciding we don't like pollution. The thing, what can you do to stop pollution, right? You need global cooperation to stop pollution, right? If you decide, as Israel decides not to pollute anymore, we're not going to affect anything in the world, right? We can decide that we legislate against Bitcoin mining, it's not going to be effective, right? This protocol, once released, is in equilibrium in a global sense. It's going to be hard for us to affect change, right? And market forces are now pulling us away. Just like cars appeared, and they have the side effect that they're doing damage to the environment, so did Bitcoin appear. It has this side effect that it's damaging the environment. You do see currencies like Ethereum that switched to proof of stake that no longer pollute, right? And after you think of switching to Ethereum, everything there is just basically transfers of money between individuals. So there's no bad effect to resources. They don't consume resources, currencies like Ethereum. And if you think about what function they play in the world, I mean, you could hold money by the US government. That gives you certain benefits, like, you know, there's dampening of oscillations in I don't know, in interest rates, in wages, in prices, right, that the central bank gives you. But there's always a risk that they will decide to be fiscally irresponsible and erode the value of your money. For Bitcoin, this is kind of like holding gold, right? It's not in anybody's power to create it without some effort. But nobody will also try to have monetary policy over it, right? So that's also, and then as a person investing in stuff, maybe you want both asset classes to exist to hedge against certain events or whatever. So it's never, I don't think it's ever going to take over the world and become the only money and so on. But it does teach us a lot of lessons about how money works and what we could do. And I think we'll see more of them actually tomorrow when we forget mining. Mining is, you know, how this thing works under the hood. How it works in the higher layers is something that we can actually very easily take to current financial systems and learn from.